recall the definitions what we have seen in the beginning. F of x equal 3x plus 1. Here the delta is epsilon by 3 for any given epsilon. Therefore, this function is uniformly continuous on entire real line. Whereas we observed from the graph of G could not be uniformly continuous, but we can apply theorem 11, the sequential criterion for non-uniform continuity, by finding one suitable epsilon. For this epsilon naught, which is 2, and if we take these two sequences n and n plus 1 by n, this function g of x is not uniformly continuous or not, because distance between x and yn, so here we are in the set of real numbers, the distance between x and yn, which is modulus of xn minus yn, which is 1 by n tends to 0. But if we calculate modulus of g of xn minus g of yn, which is greater than or equal to 2 for all n, therefore this function is not uniformly continuous on R. But this function is uniformly continuous on a bounded set minus 10 to 10 or any bounded set. You can prove it easily, because we have observed when the values are increasing, when x values are increasing, the corresponding delta from our conception becomes smaller and smaller. But if you are taking a bounded subset of R, say for example minus 10 to 10, then we can find a bound for this x plus y which is less than or equal to 20 for all x, y. Therefore, this delta is depending only on epsilon. In this case, this g becomes uniformly continuous on this bounded set, and moreover one can prove easily this function is uniformly continuous on any bounded subset A of R. Note that this function is not uniformly continuous on the entire real line, but this is uniformly continuous on any bounded subset of R. The next example we have seen, h of x is 1 over x square, which is continuous on the open interval 0 to infinity. This is, we could not get a common delta for any given epsilon. Delta was depending on the choice. But here one can prove easily this function is uniformly continuous on any set of the form closed A to infinity. So the proof is given using epsilon delta criterion. For any epsilon greater than 0, we need to find a common delta satisfying this. By finding the difference between hx and hy, we can get this. So only we need the upper bound for y plus x over x square plus y square. But if this is possible, if we could get the bound for y plus x over x square plus y square over the interval a to infinity, then we will be able to get delta, which can be taken to be epsilon by m. This one can observe easily, because if I choose any point in the set, every point is more than a. Each real x in the set is greater than or equal to a. Using that relation, we can prove that this quantity is less than or equal to some bound. Here the bound is 2 over a cube. Remember, a is fixed. A is fixed, which is a positive constant. Therefore, this function h of x is uniformly continuous on closed A infinity. Remember, since epsilon depends only on epsilon, since delta depends only on epsilon and the set A to infinity. In the next slide, you can easily prove by using epsilon delta the function g is not uniformly continuous on closed 0 infinity by considering one epsilon. So if I choose epsilon naught is 1, then we are going to find out 2 points in the set x and y, but we wish to choose these 2 points x and y depending on delta. So for any delta, if I calculate this difference is this. Therefore, if I choose my x is greater than 1 over 2 delta, then this relation happens. So each one, this quantity 2x delta is more than 1. So delta square is non-negative. Therefore, this quantity is greater than or equal to 1. So here x is any point which is more than, which remember this point x is depending on delta. And then the next point we have chosen as x plus delta, that is also depending on delta. Therefore, there is no delta that works for every x in the infinite interval. Therefore, this function is not uniformly continuous on closed zero infinity. Similarly, the function h of x is equal to 1 over x square on the set 0 to 1 is not uniformly continuous. One can prove by using epsilon delta criterion. For epsilon naught is 1, we will be able to find, and for any delta greater than 0, we can choose x as delta and y as delta plus delta by 2. For these 2 points are depending on delta. If we calculate modulus of h of x minus h of y, then by simple calculation one can show this quantity is greater than or equal to 1. And as delta, for any delta, because we are considering the set open interval 0 to 1, therefore it is enough to prove this delta in the interval 0 to 1 by 2. You don't need to prove for any delta because the set where we want to know the uniform continuity of h is just open interval 0 to 1. So here we were able to identify one epsilon naught, and for any delta in the interval 0 to 1 by 2, we could find 2 points delta and delta 3 delta by 2, such as modulus of h of x minus h of y is greater than or equal to 1. Therefore, this function is not uniformly continuous on open interval 0 to 1. And next, you can find an exercise. We have seen an example in the beginning of the lecture, which is 3x plus 1. We proved that that function is uniformly continuous on the entire real line R. But what about the polynomials of higher degree greater than 1? They cannot be uniformly continuous on the entire real line. Similarly, logarithmic function is not uniformly continuous on its full domain. Similarly, exponential function is not uniformly continuous on R. You can use one of the criteria to prove these statements shown in the exercise 16. Already we have observed the function h of x is 1 over x square, which has a bounded domain that is continuous. So we have seen this function is not uniformly continuous. So by using the sequential criterion for non-uniform continuity, by constructing two sequences and finding an epsilon naught, this sequence is not uniformly continuous. Similarly, the function sine of 1 by x is a bounded function and as well as continuous function on open interval 0 to 1, but which is not uniformly continuous on 0, 1, because this function changes its values rapidly near 0. So it oscillates between minus 1 and 1 near origin. One can prove the sine of 1 by x is not uniformly continuous by constructing two sequences and taking epsilon naught as 2. For those two sequences xn and yn, modulus of xn yn tends to 0, but a simple calculation you can find modulus of f of xn minus f of yn is 2 for all n. Therefore, this function is not uniformly continuous on open interval 0 to 1. Similarly, cos of 1 over x is a bounded function and it's a continuous function on open interval 0 to 1, but it is not uniformly continuous on open interval 0 to 1. Now, we are going to see a theorem which is called uniform continuity theorem, which says a continuous function on a compact subset of a metric space is uniformly continuous. So, but we have seen some examples that the bounded domains are not sufficient. So, if at all if you want to construct a function which is continuous but not uniformly continuous, you need to go for a non-compact sets. You need to check on non-compact sets such an example is possible or not. Here just we are recalling the definition of compact set. A subset K of a metric space is said to be compact if every sequence in K has a convergent subsequence that converges to a limit in K. There is an equivalent characterization in some of the textbooks. So this definition is taken as a definition of compact set, but one can prove easily these two definitions are equivalent by using open cover. What do you mean by open cover of a set? Which is you have a collection of open sets whose union contains a set, then the set has an open cover. So for if a subset of a metric space is said to be compact, if every open cover has a finite subcover. So there are some observations. If a set has finitely many elements, obviously every open cover has a finite subcover because there are finitely many elements. Therefore, this set is compact. So compact subsets of metric spaces are closed, and closed subsets of compact sets are compact sets. In Euclidean space, the compact sets are precisely closed and bounded. This is the famous Annabelle theorem. Now we are going to prove an interesting result, which is nothing but uniform continuity theorem, which says if you have a continuous function on f is continuous on a compact set K, then f must be uniformly continuous. So suppose this is given that f is continuous on the compact set K. Suppose f is not uniformly continuous. Suppose f is not uniformly continuous on K. Then there exists an epsilon naught greater than 0 and two sequences xn yn in K such that d of xn yn tends to 0, but rho of f of xn f of yn is greater than or equal to epsilon naught for all n greater than or equal to 1. But these two sequences xn and yn are in K, but K is compact. Therefore, these two sequences have convergent subsequences. This xn has a convergent subsequence, say xn tilde converging to x in K. So in other words, d of xn tilde x tends to 0. Similarly, yn is a sequence in K. K is compact. There is a subsequence, say yn tilde converges to y. Therefore, d of yn tilde minus y tends to 0. Already we have d of x and yn tends to 0. Now we use the epsilon by 3 argument to prove that x and y are same. So the epsilon argument. So because this converges to 0, each one of them is converging to 0. Therefore, we can find the stage n0 for the sequence xn tilde such that after this stage, then the terms are small enough. So therefore, we should start with an epsilon. So let epsilon greater than 0 be given. So don't get confused with this epsilon naught, because this epsilon naught is 1 which gives this conclusion. So there exists an epsilon naught and there are sequences, we have this. So this epsilon naught, epsilon is different. So let epsilon greater than 0. So now I am using the convergence of the sequence xn tilde to x. So there is a stage n0. There is a stage n0 such that d of xn tilde comma x is less than epsilon. Similarly, there is a stage n1 such that distance between yn tilde and y is less than epsilon. Similarly, there is a stage n2 such that distance between x and yn is less than epsilon. So if I want to have all of them, therefore I need to find a stage for it. Therefore I choose n as say n3 as maximum of n0, n1, n2, n0, n1, n2. So now I calculate d of x comma y. By using triangle inequality, we have d of x comma x n tilde plus d of xn tilde yn tilde plus d of yn tilde y. So from this stage onward, this is less than epsilon. So therefore less than epsilon. And remember, this xn tilde is a subsequence of xn. So for those n we have this, the subsequence, therefore this stage is enough. And for this we have another n2. So this is also less than epsilon from this stage n1 onwards. Less than epsilon, this is 3n, 3 epsilon. This is true for all n greater than or equal to this stage n3. But I want to have an epsilon here. Therefore we could have done this for epsilon by 3. So if I choose if I apply the definition of convergence for epsilon by 3, epsilon by 3, epsilon by 3, then instead of 3 epsilon, so we could get these stages n0, n1, n2 for this particular epsilon by 3. Therefore we can make the entire relation as the inequality as epsilon for all n greater than or equal to n3. Remember, the left side is not depending on n, it is independent of n. So, but this relation is true for any epsilon greater than 0. So, what is the conclusion we have? D of x comma y is less than epsilon for any epsilon greater than 0. Therefore, this quantity must be 0 because D is a metric. when it is 0, then x and y must be same. X and y are same. What is the advantage of x and y are same? So now we can use the assumption of continuity on the compact set. Thus we have constructed, we have identified two sequences x and tilde and y and tilde. They are all subsequences of xn and yn. So this xn is converging to x, x and tilde is converging to x, y and tilde is converging to y. So what we have seen is x equal to y. Therefore both of them are converging to the same point. Since x and tilde is converging to x and y and tilde is converging to y, and these two sequences are in the compact set K, and K is compact which is closed, therefore x and y are in K, and f is continuous on K, therefore this f of x and tilde is converging to f of x, and f of y and tilde is converging to f of y. X and y are same, both are converging to same limit f of x, because f is continuous on K. So this gives a contradiction to the relation star. This proves that this function, because we started with the f is not uniformly continuous on K, so this contradiction proves that f must be uniformly continuous on K. So there is another alternate proof by using cover, by using the definition of compact set every open cover as a finite subcover. We are going to give another proof for the same result. Let us start with an epsilon. Let epsilon greater than 0 be given. So I need to find a cover for the compact set K. So for each u in K, because f is continuous on K, so there exists delta. Delta is depending on epsilon as well as u, so I write delta suffix u greater than 0 such that d of x y, d of x u less than del u, where u is in, x is in K, implies rho of f of x, f of u is less than epsilon. So for every point in the compact set, for every point u in the compact set K, we can get a delta. Which is denoted by delta u. So this delta is coming from the continuity of f at u. So at every point in the set K, we can find the open set containing u. We get an open cover by considering the radius as del u by 2, because for a computational purpose at the end we require less than delta or less than epsilon, so we are doing the adjustment now. Otherwise you can start with an epsilon here, later you can rewrite this as epsilon by 2. You can do redo this and then check whether any extra weights are needed or not. So there are points, because there is a cover. The cover is denoted by D, which is a collection of all open balls centered at u radius del u by 2, and u is varying over K. So this is an open cover of K. Since K is compact, it has a finite subcover. Here the cover has a center because there are finitely many points in K. K is a subset of union of I is 1 to K, B of Gx of Uy and del Uy divided by 2. So this finite cover is helpful to identify the delta. So if I choose delta as half of minimum of all delta ui, I is varying from 1 to k. Let us see whether this delta, the choice of delta, is enough to say the function is uniformly continuous on k. So now we choose two points, arbitrary points x and y in k, such that d of x comma y is less than delta. So these 2 points are in k, the distance between them is less than delta. Delta is of times minimum 1 by 2 times minimum of delta ui's. So now I take the first element x, arbitrary element, so I take x is in k. So as finitely many balls cover the entire k, therefore this x must be in one of the balls. Say x must be, x is in a ball centered at ui, it is del ui by 2. In this case, we have d of x comma, this implies d of x comma ui is delta ui by 2. Okay. Now let us find distance between y and ui. By using triangle inequality, we have distance between y and ui is y and x and ui. But this quantity is already, we have taken it as less than delta, and this is delta ui by 2. So the delta is this, therefore one can show this is less than delta ui. So since the function is continuous on the set k, for every u, so this one can see, every u we can find delta u such that every x in k, delta d of x comma u less than delta u implies rho of f of x my f of u less than epsilon by 2. We use this relation 1 twice, then we can make rho of f of x my f of ui is less than epsilon by 2, and this is also less than epsilon by 2. Again, by using the triangle inequality, one can easily show this rho of f of x and f of y is less than epsilon. So we could get a delta, so which makes this relation, which makes the rho of f of x and f of y less than epsilon, and for this function is uniformly continuous on entire k. Now, on a non-compact set, in the case of set of real numbers, if the set happens to be a bounded set, then always we can find a continuous function which is not uniformly continuous. This is guaranteed. If you have a non-compact set which is bounded, but this is always guaranteed. So how do we consider? Suppose a set is bounded and it is non-compact, so it is not closed, then there is a limit point which is not a point of e. Then consider this function f of x is equal to 1 over x minus x naught. You can show this function is continuous, but it is unbounded, and by using this epsilon delta criterion, you can show this function is not uniformly continuous on E. But we cannot say anything about if the function, if the set is not bounded. It may happen that on an unbounded set, every continuous function is uniformly continuous. So this is an example. you take set of integers, and which is a subset of set of real numbers. So we take in the set of real numbers the discrete metric, the usual metric, the usual distance. So in this set, if you take any function which is uniformly continuous, because we can take any number less than 1 as for delta for the definition of uniform continuity. So this function is unbounded, but every function defined on the set is uniformly continuous. Now the next example says, what about uniform continuity of sine and cosine functions? So they are uniformly continuous on the whole real line, because by using the uniform continuity theorem, we can easily see that these functions are already continuous on the entire real line on this closed and bounded interval -pi to pi. Then this set is, these two functions are uniformly continuous, and by the 2 pi periodicity, because we need to show for any x and y in R. So if I start with any epsilon greater than 0, we choose delta such that this happens, because we know it is uniformly continuous on -pi to pi. So if I choose any other points x and y in R, then we can find a and b in the interval -pi to pi, such that this happens modulus of a minus b less than modulus of x minus y, and sin x is sin a, sin y is sin b. Therefore the same delta is suitable for any x and y. So this proves that both sine and cosine functions are uniformly continuous on the whole real line R. Similarly, you take any continuous functions on the closed and bounded set. So in this example, all of them are uniformly continuous. So exponential function, polynomials, we have seen they are not uniformly continuous on their entire real line, but they are uniformly continuous on every bounded set. Because you take the closure of the set, so then it is closed and bounded, which is compact. So this bounded set is, which is a subset of that closure, which is also uniformly continuous, because on the bigger set we are able to get a delta, then on the smaller set the same delta is useful. For exponential function and all polynomials are uniformly continuous on every bounded subset of R. What about tangent function? The tangent function is continuous, but it is not uniformly continuous in the interval. The reason is this function is not continuous on any superset of this which is compact. But if I choose any R in the interval 0 to pi by 2, then the tangent function is uniformly continuous in the interval, because it is continuous on the closed interval. Because the last closed interval, which is a subset of this, but which is closed and bounded, compact, therefore this tangent function is uniformly continuous in the interval. And if you choose a discrete metric on X, suppose there are two metric spaces and f is a function from x to y, but we choose d to be a discrete metric, then f is uniformly continuous irrespective of any metric. Because if you choose any delta, so the distance between x and y is less than delta, and delta greater than 0 means x and y are same. When x and y are same, f of x and f of y are same, then rho of f of x comma f of y is 0, which is always less than epsilon. Therefore this function is uniformly continuous irrespective of any metric on y. And there is another simple exercise. What about the sum of uniformly continuous function? Suppose there are two functions, they are uniformly continuous on some subsets say A and B, then the sum is f, the sum of the two functions f plus g, which is uniformly continuous on the common domain. And similarly, in a similar way, you can also prove the composition. So if there are two metric spaces, f and g are uniformly continuous function on x and fx, then G composite F is uniformly continuous on X. So this part ends with some exercises. So please try to solve on your own. 1 over x is uniformly continuous on 1 infinity, closed 1 open infinity, and similarly one can show 1 over x power n is uniformly continuous in the same interval, and but this function 1 over x on the interval 0 to 1 is not uniformly continuous. So you are asked to prove this by using epsilon delta criterion and this sequential criterion for non-uniform continuity. But this function f of x is uniformly continuous on the set a to infinity. Already a proof is given for 1 over x square in the interval closed a open infinity. So you can also try for the function 1 over x. In the second example, exercise says prove that this function 1 over 1 plus x square is uniformly continuous on R. And similarly, the sum of two uniformly continuous function is uniformly continuous, the composition of uniformly continuous function is uniformly continuous. But here, these two functions are, for a composition, the two functions are taken to be uniformly continuous on the entire real line. Otherwise, you could have chosen uniform continuity on a set and its image. That is also possible.